Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues. Welcome to the public doctoral defense of Xinyuan. I declare the session open. Ik heet u van harte welkom op de openbare doctoraatsverdediging van Xinyuan en verklaar de zitting voor geopend. Mr. Deng behaalde een Master of Engineering in Architecture aan de Southeast University in China. Hij heeft aan de faculteit Ingenieurswetenschappen een proefschrift voorgelegd met de titel Kwaliteitsbeoordeling van warmte, lucht- en vochtmodellen, HAM, om het hygrothermisch gedrag van bouwcomponenten te voorspellen en dit tot het verkrijgen van de graad van doctor in de ingenieurswetenschappen. Mr. Deng obtained a Master of Engineering Architecture at Southeast University in China and has submitted a thesis to the Faculty of Engineering Science titled Quality Assessment of Heat, Air and Moisture Models to Predict the Hygrothermal Response of Building Components, as part of requirements for the degree of Doctor of Engineering Science PhD. He will now proceed to defend his thesis. Mr. Deng, you are invited to give a presentation of approximately 45 minutes about your work, and following your presentation there will be time for discussion of your work with the members of the examination board, which I will present later, and with the audience. Xinyuan, ik verzoek u eerst een uiteenzetting van ongeveer 45 minuten te geven over uw werk. Daarna zal er gelegenheid zijn tot het stellen van vragen en het maken van opmerkingen. The floor is yours. We'll have a photo up after the proclamation too. Okay?
So, hello everyone. My name is Xinyuan Dang. I'm really glad to have all of you here for the final presentation of my PhD research. So this work was started from 4.5 years ago, from September 2021, supervised by Professor Staff Roos as the corresponding supervisor and Professor Hans Janssen as the co-supervisor. So before I start, I should say good afternoon for everyone sitting in this room, and at the same time there are over 100 participants joining this session online. So I would say good morning for people from Canada, America and Brazil, good afternoon for people in Europe and Africa, good evening for people from East Asia and Oceania. So this is not just a greeting for the presentation, but also the start of my presentation. So we are living in the same world, but the differences in time, in space, in the environmental exposures, all these factors are shaping our different behaviors, not only for us human beings, but also for the building components, for the building environment. So as we all know, the heat, air, and moisture transport through the building components are crucial to their durability, their performance and resilience. Here I have a few examples for the environmental risks, their degradation, deterioration risks related to the heat, air, and moisture transport. In order to evaluate these HAM transport, a range of factors should be determined. The two main factors that we need to know are the material properties and the boundary conditions. So for the boundary conditions, they are referring to the weather data on the indoor side and outdoor side, including the temperature, relative humidity, solar radiation, wind driven, and so on. And for the material properties, they are referring to the heat and moisture storage and transport properties, which defines the capability of the material can hold or transport the heat and moisture going through them. Of course, we need to know other factors, including the dimensions, geometry, initial condition, and also time steps, grid discretizations for the numerical modeling. Nowadays, we have a range of HAM models to run the simulation to know the hygrothermal behaviors of the building components. And all these models trace the same origin to the basic theories and equations. For example, the Glaser method, which is a one-dimensional steady state formula that simply compare the vapor pressure and the saturation vapor pressure at the interfaces of the materials. It's quite simple. And nowadays, for the more complex HAM models that we are using now, they consider the transit, process, coupled transport, moisture storage, dynamic boundary conditions, and also consider the material interactions. Among these models, WUFI and DELPHIN are the two primary software that we are using now. At the same time, some people, practitioners or researchers prefer to use their personal codes via different languages, platforms, and so on. And HAM models are not only limited to heat, air, and moisture transport. Some of these models also integrate the transport of VOC, salt, and some of them are integrated in the building energy model and CFD and so on. I can show you a few user interfaces of the typical HAM models, and these interfaces are from WUFI. So, as you can see here, it follows a quite user-friendly workflow. The user can just go from step 1, the material properties, the boundary condition, and so on, and then determine each of these inputs and ask for the outputs. Why do I see here data inside out even for non-expert in HAM modeling? That is because, for instance, here in the middle of this page, there are two built-in databases of the material properties and also the weather data. So if you are not doing a measurement of the material property and the boundary conditions, you are still able to choose the material properties which you think is more with the similar properties as you actually in your building structures, and you can easily pick up weather data at a specific location near your buildings. And then WUFI is able to generate the results, the hygrothermal responses, as line chart, as whatever. Similar for DELPHIN. DELPHIN is more dedicated for scientific use, but it's still a user-friendly model. This model seems to be perfect, as they can always run the simulation and prove that the data, whatever they are correct or not. So why I show this cow here? Because there are different assumptions, simplifications, and approximations made during the model implementations by the model developers. So that means we as users, we have no idea about what is really going on behind the user interface. So we cannot always trust these models. This brings us to the research question about this PhD. So the question 1, what factors are responsible for the deviations in the simulated hygrothermal responses? As I mentioned before, the two main factors are boundary conditions and material properties. Question 2, how sensitive are the simulation outputs to these uncertainties in the inputs, which constitute the main body of my PhD? And lastly, how can we improve the implementations? How can we address these uncertainties in the inputs to get more reliable outputs? This framework shows the overview of my PhD. So from the basic introduction and state of the art, we come to part 2 and part 3, which deals with the uncertainties due to the implementation of material properties and boundary conditions. And then I draw the conclusion with some useful suggestions for both model developers and the users. And on the right are the main scientific outputs of my PhD. There are 5 journal papers and 5 conference papers. Now let's move on to the part 1, state of the art. Yeah, let's welcome the cow again. So Before we start the HAM modeling, we need to determine a range of inputs, including dimension, geometry, initial conditions. Just as I mentioned before, the material properties and boundary conditions are the two main crucial parts that we need to determine. Then we don't know what is really going on behind the user interface. Then the HAM model can just bring you the outputs, the hygrothermal responses, as raw data or as the illustrations. Actually, I'm not the first person to do the quality assessment of HAM models. So how does this work? It's quite simple. We just need to compare our simulation results with the correct answer. With the correct answer, which means what we have measured in the experiment. We assume that the experiment is always reliable. Yeah, we can discuss it a bit later, but now we just put it here. The second choice is to compare the simulation results from different models. So from the beginning, we have the measurement for the inputs in the modeling. We have the material property, boundary condition, and so on. At the same time, we also have measurements of the hygrothermal responses to derive the measured data. On the other hand, with these necessary inputs, the HAM models are able to run the simulation and get the simulation output of hygrothermal responses. If you run the simulation by using different models or made by different users, we are able to get results from different models. So whether they are equivalent. So these are the two main approaches. From the literature review, there are more than 7 experimental datasets to do the quality assessment of HAM models, but they suffer from common limitations. For instance, the scale restriction, material monotony, simplified hygrothermal responses, and incomplete documentation. That means the researchers afterwards cannot repeat this quality assessment. For the quality assessment made before, there are more than 28 publications using different methodology to do the quality assessment. The first one is verification, which means the model is typically done by the model developer. They compare their simulation results with the analytical solutions. The second one is validation. It's a comparison between their simulation result and the experimental dataset. And lastly, we have intermodal comparison. Just as I mentioned before, we can just compare the simulation result from different models. To address these limitations in the previous datasets and also the quality assessment efforts, in this PhD, it develops a stepwise quality assessment protocol. There are 2 dedicated datasets introduced. The first one is the in-lab benchmark dataset. So that means we do the measurement in the lab and make the boundary condition as simple as possible. So that means in this case, the main uncertainty is the implementation of material property. And secondly, we have the in situ benchmark datasets in the real climate condition. We do the full material property characterization as well, but the main concern here is the implementation of wind-driven rain as the main boundary condition. Why do I say this research is comprehensive quality assessment? That is because it integrates both the experimental validation and also the intermodal comparison. Now let's move on to part 2, under the controlled boundary condition, which is based on the hotbox codebox lab test. So this hotbox codebox setup is based on the experimental facility in our section. So you can first take a look at the figure on the right. So we have the code box in blue on the left, and we have the hot box in red on the right. And we also have the rainbow colored. Board, mineral wood. So in between, at the interfaces of these material layers, then we are able to get the hygrothermal. For the boundary conditions, they are fixed in code box and hot box. So in the code box, the temperature is 2 degree, 8 a bit more complicated. This measurement lasted for 2 months, and in measurement for the surface transport coefficient to determine the surface moisture. The largest challenge is the material heterogeneity. That means even for the same material, for instance, liquids or natural heterogeneity. On the other hand, we have more challenges in data processing. Are not always the same in the hygroscopic range. And which one should we rely on? That's a challenge. And secondly, the transformation have to multiply the liquid diffusivity with the slope of the moisture retention curve. That means the uncertainties in the empirical equations. Let's take the liquid diffusivity for example also. Here, waterfront were not able to get the liquid transport properties from the measurement, then we should refer to some alternatives. For instance, the but these equations are not always reliable. Then the second part, the data processing from the determine the vapor transport properties. So if you take a look at the figure on the top right, so we have salt solution in the cup, which regulates the relative humidity in the cup, and this cup with this material is placed in a climate chamber. So that means in the chamber the relative humidity is also controlled. So we have the difference, relative humidity difference between the cup and the chamber, or let's say the vapor pressure difference between the cup and chamber. There will be a vapor flow upward or downwards. Then we are able to calculate the vapor resistance factor, the mu value. And then we can repeat this similar measurement at different relative humidity difference to derive the mu value as a function of relative humidity. These are the measurements. But in the actual implementations, there are several ways to implement the raw data. The first assumption is to split the vapor transport term from the measured data. So that means in the raw data, it not only considers the vapor transport, there is also the contribution from the liquid transport, especially in the high relative humidity range. So this assumption assumes that the vapor transport is constant throughout the process. If we do the mathematical translation from the mu value to kV, we can do the similar simplification for vapor permeability as a constant value. The second typical assumption is to consider the pure vapor transport in the high moisture content range. So as you can see from the third figure to the fourth, the vapor pores hold more liquid moisture. There will be limited space for the vapor to go through. That means the vapor transport will be reduced. The liquid transport properties are more complicated. So from the measurement part, typically we can do the X-ray or NMR or the ruler method to determine the moisture content profile as a function of X multiplies the square root of time. And we can do the Boltzmann transformation to derive the liquid permeability dW as a function of moisture content. Yeah, it behaves like this. It decreases a little bit in the low moisture content part, and then it increases. But not everyone has the devices of X-ray, NMR, and not all the materials allow us to run the ruler method to derive the measurement result. If not, what should we do? The primary choice is the Kunzung's formula, as I mentioned before. It's based on the AW, the capillary absorption coefficient, and the capillary moisture content. So you can simply get this linear curve in log scale by using these two parameters. It's quite simple, but not always reliable. If we do the mathematical translation from dW, the liquid diffusivity, to KL, the liquid permeability, as I mentioned, we should consider the slope of the moisture retention curve. So the deviation persists and maybe be even larger. The same for moisture storage. So typically we do the desiccator test, the MIP test, sometimes the pressure plate test, which takes more time. Here I have an example for the results from desiccator test and MIP test. So the crossings are results from the desiccator test. That means we place the sample in the soft solution for 1 month or 2 months to make sure that the moisture in the pores is in the equilibrium state. Then we are able to determine the equivalent moisture content at specific relative humidity condition. At the same time, we can do the MIP test, the mercury intrusion. We are able to generate a similar curve, but it's continuous, particularly for the over hygroscopic range. So if we enlarge the over hygroscopic range, typically from 97.4 something relative humidity, you can clearly see the deviations between both. These are the measurements, but for the implementations, these are not always the case. So the first assumption is typical for the engineering scenarios. So for engineers, they don't have MIP. They don't do the MIP test. It's expensive, complicated, but they can do the desiccator test. Just put the sample to the soft solution for 1 month or 2 months, much easier. So they have no information about the over hygroscopic range. What they can do is just to linearly connect the last point from the desiccator test to the separation, moisture content. That's the first way. So for the second one, that's what we typically do, because we have all the facility. We are rich. We have all the facilities for this characterization tests. We do both the desiccator test and also the MIP test, so we are able to connect both. Sometimes these results are not always overlapping, and we need to do further simplifications like shifting or scaling to make sure they are smoothly connected. The third approach is implemented in WUFI. So it's quite simple. It's just based on 3 typical reference relative humidity conditions. So if the user implements the moisture content at 80% and 100%, that means they call the reference relative humidity and the saturation moisture content, we can generate this curve, the dotted blue curve, automatically. That's quite silly, right? So it can generate this curve purely based on 1, 2, 3 points. So that means when the relative humidity is lower than 80%, that means their 2-point method will underestimate the moisture storage significantly. Now they introduced another approach called 3-point curve. They argue that this method is more reliable. They consider the issues in the over hygroscopic range. If we translate the moisture storage curve as a function of the absorption isotherm to the moisture retention curve, the deviations among these curves from the measurement to the implementations, they persist and even be larger. So let's go back to the measurement. How do we make use of the measurement for the boundary conditions, material properties, everything from the hot box, cold box test? So from 2023 to 2024, we have coordinated the largest collaboration on HAM model assessment. There are more than 70 persons from 38 groups from 19 countries participated in this international collaboration. What we did there, so this is stepwise round robin validation. How it works, it consists of 3 stages. The idea is that we have all the measurement of inputs and outputs, but we only send out the result of the inputs to the participant to ask them to run the simulation to get the outputs. And then we collect their outputs to compare their outputs and our outputs in the measurement to see whether their models can work well to predict the hygrothermal behavior of the wall assemblies in the hot box, cold box test. So in stage 1, it simulates an engineer scenario. So you can see from this table, the biggest issue is the material properties. So in stage 1, what we provide to the participants, these are the technical sheets from the material producers. We receive this raw data of the material properties and we send out this information to the participants. And the material properties within these sheets are not that complete, especially for the moisture storage and transport properties, which are crucial to the HAM modeling, but they are absent. From stage 2 to stage 3, we provide them with the material properties that we measured in the lab, and in stage 3, we provide them with the hygrothermal responses that we have measured in the hot box, cold box chamber to allow them to adjust their implementations to make sure the deviations from their outputs and our measurements become closer. Let's invert the cow again. So when the participants receive our measured inputs, they are able to run the simulation by doing some translation from the measurement to the implementation. Then these models are used by these users, and these models are able to provide us with the simulation outputs. DELPHIN and WUFI are the 2 primary choices by the participants. These are the measured outputs that we have, and then we collect the simulated hygrothermal responses from the participant to compare these 2 datasets to see whether their model perform well. Now I can show you a few examples for the results. On the left, we have the implemented moisture storage properties. So first we have, I'm not sure whether you can see this black crossing clearly. So these black crossings are results from the desiccator test, and for the green circles are from the mercury intrusion test, and we also have the weak acceleration test to determine the moisture the ending point of the curve. So as you see here, these are the results from DELPHIN, WUFI for calcium silicate mineral wood fiber, showing both in the function of sorption axiosome and moisture retention curve. And you can see that these curves are not overlapping always, and there are still some obvious deviation between them, especially for that one, the first one. There is one curve entirely overlapping with the data from the MIP test. That means, as I mentioned before, we typically assume that the mercury intrusion is not always reliable in the hygrothermal responses. So that means the moisture storage in this range will be systematically underestimated. And what are the impact of this deviation in the inputs? If we take a look at the graph on the right, these are the relative humidity predictions compared with what we have measured in the measurement. So the black dots are the measured results from the whole box test. And all these curves are from the participants. And you can clearly see the deviations are quite large, even up to 60 or 50 or 60% relative humidity. Similar for these are the typical ways to implement the moisture storage properties. So these are the conceptualized image to show the way that people implement moisture storage properties. Similar for the moisture transport properties on the left. So we did cap test for the vapor transport properties. We did the ruler method by using the capillary absorption test to determine the liquid transport properties. That's what we provide to the participants. And you can also clearly see the deviations between what we have measured and what people actually implemented. And by the way, there are still some green crossings, which indicates the provided data from the technical sheets by the producers. And if you compare the results from the technical sheets and what we have measured in the measurement, these data are not always the same. Let's move on to the main conclusion from this round-robin validation campaign. So basically, for the heat-related responses, for the temperatures and heat fluxes, both of them are well predicted. There are more difficulties in modeling moisture-related responses. They are more sensitive to the implemented moisture transport and storage properties. More specifically, in stage 1, we only provide them with basic information from the technical sheets. So the users can only rely on the reference data. So that means they can pick up the material entries from the built-in database or any publications to do some data processing to get the, let's say, so-called similar material in their models. And we also noticed the difference between the claimed material properties from the producers and what we have measured. This fire link plot shows the deviations of the material properties of the claimed value from the producers in the red crossing and the actual implementations from the participant in stage 1. Stage 2 and stage 3, in these two stages, people receive all the measured material properties and they are able to do the data processing. And this highlights the uncertainties in the translation from the measurement to the implementations and the impact of these uncertainties. So the heat map on the right indicates the normalized root mean square error of stage 1, stage 2, stage 3, or assembly 1, 2, 3, 4. So if take a look at a single box, these are the parameters of temperature, relative humidity, heat fluxes, and moisture masses. So basically, the bluer the better. That means each small box indicates the result from each participant on each parameter of specific work assembly. So that means it's clear to see that we have more red boxes at the bottom. These are from the moisture masses, and we still have some deviation in the relative humidities. So we have already observed the data processing uncertainties through the measure from the measurement to the implementations and their impact on the final predictions. Given that there are different models are involved in this round-robin validation, they are based on different driven potentials, are based on different governing equations. It's not that easy to make the comparisons among them. So here we introduced an equivalent moisture permeability to harmonize all these material property parameters to, by using the same ruler to measure the deviations among them. And you can see that the black dashed line indicates the result from the cup test from the measurement. These blue, green, red, and yellow curves are from the translated equivalent moisture permeabilities from different users. If we link the implemented equivalent moisture permeability and moisture storage properties with the moisture-related outputs. By using the Pearson relationship, we are able to get some idea about which factor, which parameters are more responsible for which outputs. And here we found that the moisture mass is quite sensitive to the implemented moisture storage and transport properties. So here we have suggestions for the researchers that it's significant to incorporate moisture mass as an indicator for model assessment. Because in the previous validation or assessment studies, most people will consider temperature and relative humidity as an indicator to see the agreement between their measurement and a simulation, but that's not enough because we noticed the material property have a large impact on the final predictions. Building on the insights from the round-robin validation, I myself did further investigations in the implementation of material properties in WUFI and DELPHIN by using different scenarios, using different configurations. Here, two typical configurations are introduced for the modeling. One is the internal insulated wall. The other one is the brick with mortar layer inside. There are three typical moisture exposure regimes. The first one is the extreme scenario, which includes the extensive wind-driven rain with short-term rapid temperature changes. The second one is real climate data. We used the one-year monitored weather data from the Valide building in Leuven for this real climate simulation. Finally, we have a fictitious surface condition. The relative humidity ranges from 50% to 98%, inducing partial over hygroscopic absorption. So by using these two configurations and three boundary conditions, we are able to the impact of the different moisture storage or transport properties on different scenarios. So for the main insights from this comparative simulation, first, for the implementation of liquid transport properties, we found that the Kunzung's formula for estimating the liquid diffusivity deviates much from the experimental-based data. And secondly, we also noticed that the translation from the liquid diffusivity from the permeability cannot be neglected. Secondly, we investigated the integral and separate formulation for vapor and liquid transport properties. The first conclusion is that it's necessary to incorporate independent liquid transport properties, either from the measurement, the X-ray or ruler method, or the Kunzung's formula at least. Even it's not that accurate. The second one is very useful insights for the users that delphing applies internal reductions for the mu as a function of relative humidity. That means even if we implement the same measurement data, but we implement this data in a different way. The first one is to implement the test results using the raw data, the mu value as a function of relative humidity. Delphin will do the internal reduction. It does not actually implement what we implemented. The second choice is to do the manual translation beforehand. We translate the mu as a function of relative humidity to kV. They are mathematically equivalent, but Delphin will only do the internal reduction to one of them. That means the same data inputs will, of course, generate the different outputs. Thirdly, we found that the integral or separate formulation for vapor and liquid transport properties have an impact on heat transport. For the moisture storage properties, we found that WUFI's accuracy is highly dependent on the input accuracy, while Delphin seems to perform much better, because it seems that Delphin did some internal refined interpolation if the data input is not in high resolution. For the 2-point and 3-point simplified formulas by WUFI, we found that they perform well in the over-hygroscopic range, but it's a paradox. They overestimate the moisture storage in the high. Compare with the material properties. For the wind-driven ring, it is the most crucial boundary condition in HAM modeling. Now we have different ways to calculate wind-driven ring by using different semi-empirical methods from the ASHRAE standard, from the ASO standard, and also we have alternative in WUFI. These three semi-empirical methods are similar but not always the same. As you see here, we have different parameters to consider the surrounding environment, the surface condition, the height of the building, the place of the wind-driven ring that we consider on specific facade, something like that. These formulas are similar but not always the same. At the same time, there are actual simplification in implementing this method into HAM models. And this part tackles the impact of these two factors on the final hygrothermal predictions. I'm going to show you a few examples. So for the first stage of this part, we compare the calculated wind-driven rain from two datasets, one from Leuven, another from the Netherlands, by using the three methods, WUFI 1, WUFI 2, and DELPHIN, and compare the simulation results of the wind-driven rain loads with what we have measured against the wall. And you can clearly see the deviations can be even large, but it's highly case-dependent. And if we implement the calculated wind-driven rain as the imposed flux directly to the surface, we can clearly see the deviation in the simulated hygrothermal responses of these walls. And the interesting fact is that we notice that, so here we can see the blue curve and the yellow curve, they look the same. But when we dig into the hygrothermal responses, the yellow curve, strangely brings out the most deviating hygrothermal responses. So that means we should not only consider the accumulated wind-driven rain loads in 1 year, but we should also consider the hygrothermal responses at specific locations, specific critical moments. Now let's move on to the final parts, conclusion. Due to the time limit, I don't think I need to summarize this. Let's say something about the practical insights for the users. I would highlight the uncertainties due to the material properties. I can't explain more detail, but you can refer to the page 122 to 24 for the table, which is cross-references the material types with the moisture exposure scenario, and it highlights the hygrothermal properties which are most crucial to the simulation outcome to this scenario. For the limitation of this work, there are a few factors that are not considered in this PhD. For instance, the geometry and the material heterogeneity. For the historical structures, for the composite structures, it's not always reliable to use the harmonized 1D model or 2D model. We should also consider the interactions between layers, between different materials. And the second one, for the initial condition, for the surface conditions, the simulation scenarios in this PhD are much simple. So these factors should also be digged into to see whether they have a large impact on the hygrothermal predictions. Let's invite the Carl once again. So we don't really have all the information within this Carl. There are also some algorithmic trade-off behind the user interface. But the final goal is to build a shared infrastructure for the model advancement. This is the final page of my presentation. I would like to share this image that I generated yesterday using AI. This tool is truly powerful. It captures the main idea of my research in this single picture, as this image vividly illustrates the main goal of my PhD is to gain deeper understanding of the information within the black box, enabling models to better understand and address the challenges of the built environment. Thank you.
Thank you very much for this highly interesting presentation. I will now present the examination committee, aka the jury. Before we start